Hey, you're so welcome. Life got appreciation. So nice. Alrighty, so let's look at this first one here. Are we ready? A heavy object is pulled across the floor using a force of 100 pounds. The force is exerted at an angle of 50 degrees above the horizontal. Now, here's what that means. Let me just kind of pause for a second. If you're watching a video, I apologize. Do I have a... Here, I'll use this desk. Can you guys see me? So, you've got this chair and it's going to head this direction. And I'm pulling from the top because I'm tall. And I'm going this way. And it's dragging horizontally, but I'm pulling it up is what I'm doing. So that's what's happening when it's talking about that horizontal, or the angle is 50 degrees, is it's also being pulled up. This is being pulled up while being pulled sideways. Does that make sense? So, let's get our little picture here. Heavy object, pulled across the floor. And the force is 100 pounds, and the force is exerted at a 50-degree angle above the horizontal. So here's our 50-degree angle, and here's our 100 pounds. So if it's above a horizontal, what kind of triangle is this? It's a right triangle, right? I mean, that's kind of what we have here, is we've got a right triangle. It's above a horizontal, so we do kind of have this other sort of floor here. Find the work done. Work, it tells you, is F times D, where F is the component of the force, so in the direction of motion, and D is the distance. We have distance, we don't need it yet. We've got a force here, we have a force here, we got to find this force. How are we going to do this? What? It's a right triangle. We've got an angle. I need the adjacent side, and I have the opposite, or I have the thank you. Hypotenuse, cosine. So can't we just do cosine of 50 degrees is adjacent over hypotenuse. So we have 100 times cosine of 50 degrees equals F. What do you guys get? 64.3. And they want us to find the work done. So we're not done. We found the force. We found this. Work, it says, is F times D. Force times distance. So here's our force, 64.3, times our distance of 30 feet. And that should say feet, sorry. And what do we get? Calculators, what's it say? 1928.4. Do you know what the label on that is? Any of you physics people? Foot-pounds. Foot-pounds, yeah. And it is not feet per pound. These are foot-pounds. And that's a thing. All right, let's move on. An airplane has an airspeed of 450 miles per hour and a heading of 60 degrees. In your notes, please write this word, bearing, above it. We use the word bearing for nautical, it's a nautical term for like ships. Heading is typically airplanes. It means the same thing. So if it's a heading or a bearing of 60 degrees, what's that tell us? From the, we kind of have to look at the north, right? So if it's 60 degrees, do I go east or west? You assume it's east unless it tells you west. Okay? Right? Or did I do that backwards? No, I'm right. Sorry. 60 degrees. And that's 450 miles per hour. A wind is blowing from the north. So which way is that arrow going to go? Down from the north. Good, and it's blowing, so it's blowing south at 42 miles an hour. find the plane's ground speed and its course or direction. So we're looking for magnitude and direction. So why don't we do that whole called parallelogram thing. We're looking for, or you can just draw it, we're looking for this guy right here. That's going to be the plane's ground speed. But for some of you, it's going to help to kind of extend some of these lines. That's a G. Sorry. And if you wanted to finish out that parallelogram like we did yesterday, we could do that. Remember yesterday we had that parallelogram method? Ashley's lost. Ashley, do you see how this was a little airplane right here, and don't judge my drawing? Oh yeah, that's a really bad drawing. Shh. Anyway, there's a plane. Shut up. There's a little plane there. That looks ridiculous. There's a plane there. Ashley, and this would be its direction if there were no wind, but there is wind, so it's being pushed, and this is its new course in blue. Okay? Yesterday, remember that parallelogram method we had? Where we take this vector and we slide it over. We take this vector and we slide it over. So now we have this parallelogram thing going on. And the reason I kind of extended some of these lines in pencil is it might help us find some angles. If this guy is 60, then isn't this guy right here 60? Yeah? Does that help us find anybody else? Doesn't it help us get this one right here? Is that one also 60? Because with parallel lines cut by a transversal, alternate interior angles are the same. So that's 60. Now that I've got two sides and an included angle, I'm thinking law of cosines is going to get us G. So now we say G squared equals the first side squared plus the second side squared. I'm sorry, do we zoom out? I'm sorry. There you go. Is that better? Sorry, guys. Minus 2 times the first side times the second side times the cosine of 60 degrees. You've got a calculator, type it all in. Don't forget to do the square root. Sammy, let me know what you get when you get there. What do you think? Yep, 430.5. And that's miles per hour. So that's how fast that plane can go now, because the wind is affecting it. It also wants to know its course, its direction. So now keep in mind, we were talking about heading. So it really wants to know this orange one. But in order for us to find that orange one, we're going to have to solve for alpha right there. How can we solve for alpha in there? Yeah, just like yesterday's assignment, law of sines. So, bless you. So I know that this one is now 430.5. So I have sine of 60 degrees is across from 430.5. And that's going to equal sine of alpha over, across from it is 42. You can flip law of sines. It'll help you. It just makes it faster. You don't have to flip it. You can put the distances on the top. Doesn't matter. Yeah, because you figure all you have to do is multiply both sides by 42 and then arc sine. It doesn't matter. It's all the same. Bless you. All right, I got 4.8. How about you guys? 4.8 degrees. What do I do with that 4.8 degrees? Yeah, this was 60, and I have another 4.8 degrees. So we add our 60, we get 64.8 degrees. And that's our new heading. Yes. Yeah. Like for a picture, it looks like length, but that magnitude could be force, it could be speed, or it could be an actual distance. Somebody else had their hand up? Question? Maybe it's just when we're fixing her ponytail. I don't know. All right, next page. Alrighty. A loaded large barge is being towed by two tugboats, and the magnitude of the resultant, what's that word mean? A plus B, when you're adding the vectors together. So it's not either one of these vectors, it's this dude down the middle. That's 1,000 pounds along the axis of the barge. Find the tension in the two lines, so I'm looking for this. If they each make an 18-degree angle with the axis of the barge. So the whole thing's not 18, but each of these little ones is 18 degrees. So cute. There's a couple of ways to approach this problem. I know what they want you to do. Or I kind of know what you could do. What do you guys want to do? Tell me what to do. Like, tell me what to do. Well, you know we've been working with these vectors, right? And it helps us if we've kind of got a picture to go off of, and usually we end up making one of those little parallelograms. So why don't we draw that parallelogram? I mean, you kind of know that's where we're headed. We're talking about vectors here. And this whole resultant is 6,000 pounds, so this is just one way to do it. Do we know anything else about what's going on here, angles and all that? Now that we've drawn the rest of the parallelogram? The other side. We know that this is 18, and this is 18. Or together, it's 36. So if I know that each of those little ones is 18, if I'm just looking at the top half, where the tugboat is, what angle is that? 144, how'd you get it? Yeah, 180 minus 18 minus 18. So 144 degrees. And I'm looking for x here. Can we do law of sines? Sure. So we have x over sine of 18 degrees. X over sine of 18 is 6,000 over sine of 144 degrees. Multiply both sides by sine of 18 and let's see what we get. What do we get? And does that make logical sense probably by looking at the picture? I think so. So 3154.4. What's my label on that? Pounds. Now, if you wanted to know, these girls were wanting to do the faster way, but they didn't know what that looked like. What you could have done, and this is actually what I did the first time, then I thought, I probably shouldn't teach it that way. I just made these right triangles right there. I looked at these two, and I know that halved that right there, so that this is now 3,000, and this side is 3,000. And then I said, okay, if this is a right triangle, and I'm looking for the hypotenuse now, then I just did I took 18 and I said, okay, adjacent over hypotenuse, that's cosine. So cosine of 18 is adjacent over hypotenuse, find the hypotenuse. You can do that too. That would have to be, or the barge won't go straight. Right? Or unless one of them was pulling at a force that was greater than the other. And you know that's not because the angles are the same. I guess because of this, because those angles are the same, you know that that's going to be the same force. That makes this also x. Well, I understand your question. I see where you're headed. All right, the next one. Now these incline problems, and there's a lot of them, they kind of give some kids some fits, but just know all of the incline problems, the picture is the same. What's on the incline is different. It all kind of works the same. So once you figure one of them out, you can kind of do all of them. All right, so here's what's going on. Let's read about it. It says to find the force required, not requires, sorry, required to keep a 2,500-pound car parked on a hill that makes a 12-degree angle with the horizontal. So here's our angle of inclination right here. That's a phrase you guys have heard before. The 2,500 pounds, if you look, it's already labeled for you right here, going straight down. It is perpendicular to the horizontal. And what that's referring to is the force of gravity. So it's weight on gravity. The other little guys are probably new for some of you unless you've seen this in physics, and some of you have. You've got a force that's pulling that is perpendicular to the car, like perpendicular to the incline. You guys see that right there? And I did go talk to Mr. Smith this morning because we do use different words in trig than you guys do in physics. So you physics people, that line right there is called the force normal. We just say that that's the force that keeps it where it is. That's the force that keeps the car where it is. That's what we say. And then you've got this force right here. Do you see that arrow, that vector right there? That's the force that keeps the car on the ramp. And in physics, you guys call that friction. In this case, it's static friction because the car is parked. Now, it's probably not going to use the word friction in your trig textbook or on a test. It's going to say this: find the force required to keep it on there. So it's asking for this, actually. It's asking for friction. And if you'll look, BF is congruent to AC. So you're looking for this guy right here. Okay, here's some other stuff you need to notice, and this will help you with all of these kinds of problems. We've got 12 degrees here, we've got 90 here, we have 90 here. Do we know any other angles, or can we at least figure some out? How about angle B? Do we know what angle B is? 78, right? Because 78 plus 12 plus 90, there's your 180. If this one is 78 and this one is 90, do we know this one? It's 12. What do you notice about 12? Why is that significant? Yes, she's right. It's the same as your angle of the incline. And that's going to, it happens every time. It's just the way it is. So this large triangle is actually this one kind of inverted. So if that's true, then what's this little angle down here, this little doodad? 78. So now that we've got some more angles and we've got some sides, can we solve for AC? I think so, probably. How are we going to do that? It doesn't matter what angle you come from. There's lots of ways to do this. Let's say I just want to use this 12. I'm concerned about the opposite side, and I have a hypotenuse. Opposite of our hypotenuse is what? So sine of 12 degrees is opposite over hypotenuse. Do you have to do it that way? No. Last hour we used a cosine of 78. Doesn't matter. Tell me what you get when you get it. 519.8? What's our label? Pounds. Nice job. So these incline problems end up being kind of all the same. Be careful what it asks for. Sometimes it'll ask you for the weight of the car, so it gives you all of the other information. And sometimes it'll give you all of this information and it asks for the angle. So you just kind of have to watch it. Everybody doing okay? All right. Here's a ramp problem. This time it has a crate. You figure it out. Look at the one before it as a reference. Says that the force required to hold it onto the ramp is 18 pounds. It means that friction force. So my 18 can go here. It says that it's a 74-pound crate, so that's what's acting on with the gravity right there, 74. It's asking for the ramp, the angle, and I know that this angle equals this little red one right here. So I've got a right triangle, and I've got opposite and hypotenuse. That tells me sine. So sine of theta is opposite over hypotenuse. Do arc sine, you get 14.1 degrees. And if I have this little red guy, then I've got that one. Questions? Are you sure? See lots of really wide eyes, like you're just trying to wrap your brain around it. And that's okay. Maybe you don't even know what to ask at this point. All right, let's do the next one. A ship leaves the port on a bearing of 25 degrees. Stop there. Bearing of 25 degrees. What's that tell us? It's east of north, correct? So I'm going to draw a little. That's due north right there. He's at 25 degrees, and it says that he travels 61.4 kilometers. This isn't to scale, and that's okay. Then the ship turns due east and travels 84.6 kilometers. Oops, this is really messy. How far is the ship from the port? Here's our port down here. And what's its bearing? So we need to find this distance is what we're looking for. Which we could easily find if I knew this angle, right? We can figure it out. If you kind of extend all of your lines, sometimes it's kind of helpful because then you can see kind of some parallel lines. If I redraw, which I know Ashley doesn't want to do, but if we redraw this little guy into the parallelogram, which is a method for our vectors, and that is a terrible parallelogram. Don't judge. Sorry. Those should be parallel lines. They're not, but they should be. Sorry. And we look at our angles. We've got 25 here, so can we get this one? How are we going to get this? Don't we actually know this whole angle right here? Isn't that 90 degrees plus 25? What's 90 plus 25? 115? So this one is 115. If this one is 115, what's this one? They're vertical angles, right? So it's also 115. I need to explain that?
Where's your 90?
Because this is due north, then I knew that this was a right angle. Does that make sense? Good question. So 90 plus 25 is 115. Those are vertical angles. Now I have that. So I've got two sides and an included angle, which is telling me law of cosines. So we say, she's right, d squared equals first side squared plus second side squared minus 2 times first side times second side times cosine of the included angle. We type it in our calculator and we don't forget to square root it. Love it. 123.8. 123.8 what, guys? Kilometers. Very good. So there's our distance, and now it wants the bearing. So if we could find out alpha right here, then I probably could figure out the bearing, because the bearing is this orange one, right? So let's find out little guy alpha. How do we do that? How did we do it yesterday? Law of sines. So we say, okay, sine of alpha over, across from it is 84.6, equals sine of 115 degrees over, we know D, it's 123.8-ish. And multiply both sides by 84.6. Don't forget to do arc sine. Anybody? Yep, 38.3 degrees. Are we finished? No, what do we do? How do I get that whole orange piece? Add the 25. In total, we get 63.3 degrees. And that's the bearing now. Questions? Okay. I know that we have two more on our notes. We're going to mess with those tomorrow. If I can give you your assignment, you're getting a worksheet, and also there's a couple of book pages